given a matrix A from the system of linear equation AX is equal C. Never forget this, okay? This is a system of linear equation, okay? Now, find the minimum polynomial where the determinant of A minus lambda I is equal to 0. This is a characteristic polynomial of A is lambda minus 3 to the power 4, lambda minus 5 to the power 3. This is equal to 0. Now, we know from the Cayley-Hamilton theorem, A minus 3i to the power 4, A minus 5i to the power 3 is equal to 0. Okay, because solving this, okay, let's say, okay, what we are doing, okay? That's very important. So, here I have a matrix A, okay, matrix A. From here, we calculate f of lambda is equal to 0. And here we have, for instance, lambda I. Lambda 1, let's put it here. Lambda 2 and lambda 3, suppose, okay? It's not this case here, I'm just giving an example. Okay, for one lambda, we obtain here, okay, let's put a box here, okay? You obtain rho of A minus lambda 1i. You obtain rho of A minus lambda 2i and rho of A minus lambda 3i, okay? We calculate this. From here, okay, you have a box here, okay? We obtain the ni for each lambda, and also from alpha minus ni, you obtain here. Here is the number of solution, okay? Number of solution. Of what? A minus lambda I x is equal to 0. For each lambda, you obtain solution here. And the difference means number of generalized eigenvectors, okay? Eigenvector. Okay? And also here is a number of blocks, okay? Number of solutions of this for each lambda I have number of solution. And for each lambda I have number of generalized eigenvector. Now, when from here I have my J or capital lambda, okay? From here. Now, without calculating, okay? Now, this is Jordan or lambda, okay? Okay, now, from this here, I will get my P, okay? From here, I'll get my P. Not from here, okay? It's from here, okay? J and or lambda independent of P. Then I calculate my transition and my P minus 1. When I get P and P minus 1, P minus 1 and J or lambda, then I will solve this AX is equal to C. We did a lot of problem doing this. Now, from here, I can get J or lambda, and also I get the minimum polynomial. Okay, why I'm writing this? Okay, because as I said before on the last video, okay, minimum polynomial does have nothing to do, okay, now here, okay, with J here, P minus 1, I get X, okay, X is my solution, X1, X2, X3, okay, now I get my solution of this equation. Look, obtaining minimum polynomial does not affect the answer. That's why I pointed out before, just for you to understand. Now you ask, why we study minimum polynomial? Okay, first is minimum polynomial in the literature, okay, videos and books, and also just play with minimum polynomial will reinforce okay, in concepts of Jordan form. Just is only this, okay. Minimum polynomial doesn't help us, okay, to solve this equation here. Okay. Before doing this, let's show some remarks on the blocks which we already saw them, okay. Now remember, I have lambda here, okay. Suppose the matrix A here doesn't have nothing to do with this A over here. So A minus lambda I is equal to 0, okay? This is 0. Okay? This is a power 1, okay? This is a power 1. Now, suppose B is equal, okay, lambda, 1 here and 0. So B minus lambda I is equal, this will be 0, 1, 0, 0. Now, we saw before that if I square it, okay, then I have 0, 1, 0, 1. This will be my matrix 0, okay? So this block here, 0, 1, 0, 0 times 0, 1, 0, 0, 0, okay? This come up to 0 over here. Now, attention here, an important point, okay? Look, for instance, if I have here x minus 2, okay, that multiply x minus 2, okay, for instance, this is 0, x is equal to, this is 0, okay? For x is equal to here, satisfied, and for x is equal to here, satisfied, okay? Now, this doesn't happen here, okay? You can see here that I have here b minus lambda I that multiply b minus lambda I is equal to 0, okay? This here is different from 0. This here is different from 0, okay? Because these are matrix, okay? Although the product, okay, the square is 0, does not imply that each factor is 0, only the product. That's a very, very important result. Now, let's go to the other block, okay? Now, C, just to review, okay? Now, it's lambda, 1 here and 1 here, okay? The numbers of 1, okay, is if I have n by n, the number of 1s is always n minus 1. So this is 2. I cannot put 1 here. Why? Because I have 3 columns. If I put 1 here, it's 4 columns. So that's, and then c minus lambda I to the power 3 is equal 0, as you saw before. So if we see, okay, c minus lambda I, okay, this is 0, 0, 0, okay? This is 0, 0, 0. This is 0, 0, 0, okay? That's one block, see, that's one block. Likewise, this is one block, okay? Now, this block times this block times this block is 0, although individually each factor is different from 0, okay? Now, this is, and also you can generalize, okay? For instance, 10 lambdas, okay? Then I'll put 9 ones, okay, in the super diagonal, okay? If I raise to the power 10, then it will be 0, okay? Now, there's a very, very important point here. We're going to use here to find the minimum polynomial. Okay, given a matrix A, attention, from this is a system of linear equations. Okay, don't forget, every time I'm worried about A, I have to know from where this A came. Okay, the elements of A are the coefficient of the unknowns, okay, of X. Now, system of linear equation. Okay, find the minimum polynomial where determinant of a minus lambda I is equal to 0, then I get my characteristic polynomial, okay, polynomial. And then from Cayley-Hamilton theorem, we know that a minus 3i to the power 4, a minus 5i to the power 3 is equal matrix 0, okay? Now, let's suppose, okay? Suppose here and suppose here, okay? Suppose. I have my matrix A, okay? I know the eigenvalues. I subtract A minus 3 lambda I, okay? And then I count the number of pivot. Attention, the number of pivot cannot be never equal the dimension of the matrix. So this matrix is 4 times 3 is 7, 7 by 7, okay? Now, do you know why? Because, okay, suppose you have a matrix here, okay? I have 3 columns and I have 3 pivots, okay? So when I solve a system, okay, is equal 0, because these columns are linearly independent, okay, the only solution is trivial solution, okay? Remember, this is not A, this is A minus lambda I. So this matrix here, okay, the number of pivots, suppose here is 3 by 3. You'll never be 3, okay? Has to be less than 3. Okay, if I n by n, it will be less than n. Why? Because I want the non-trivial solution. That's all, okay? Now, suppose the rank of A minus 3i is 5, okay? Now I calculate ni, okay, is n minus 5 is 2, and alpha minus ni is 2. This I have two solutions, plus 2 eigenvectors, and 2 blocks, okay? Now, here, okay, suppose I have my matrix, I subtract 5i, and then I count the number of pivots. I count it is 4 independent columns. So ni is 7 minus 4 is 3, and here alpha, the multiplicity, okay, alpha minus ni, 3 minus 3 is 0. So here I guarantee no generalized eigenvector, For what? For lambda is equal 5. So, and here I have 2 generalized eigenvector, okay? Just from here, look, and from here, knowing the dimension, I get all this information, okay? Without calculating the columns of the transition matrix P, okay? Now, let's see all the possible J's. Let's see. Look, I have 2 solutions and 2 generalized eigenvectors. So I have to put 2 number 1 on the superdiagonal because I have 2 generalized eigenvectors. Okay, let's write a possible J. I said possible J. Here's 2. Let's put 3, I'm sorry. Sorry. This is 3, okay? This is 3, okay? The multiplicity is 4. Now it's 5. 3. Okay, 3, 6, and 7. Okay? This is my matrix. Now, I have to choose, okay, the ones, see, to put over here. So, this here is one solution, okay? I have 2 generalized eigenvector, or I put over here another solution, okay? Now, if I put here, you see, I have 2 blocks here. I have this block and this block, okay? So, this I cannot do it. Why I cannot do it? You see, because, okay, suppose I have a solution of 2 blocks, okay? I can do it, I'm sorry, I can do this, okay? I have 2 blocks. And also, I could have, just for lambda is equal 3, okay? I could have a possible j. Let's put here j, 3 and 3, okay? Now I can put one here, okay? Also I can put one here is another one, okay? Now let's do this. I have 4 here and 3 here. Now let's get this one. I'll put one here and one here, okay? Just 2, okay? Now, then I'll discuss the other possible for j. Now let's, for lambda is equal 5. For lambda is equal 5, I have 3 blocks. You see, here I have 2 blocks. 2 blocks. Let's put the 2 blocks here. Look, this is one block. See, this is another block. You see, just from here, I wrote 2 blocks over there. Now, let's see for lambda is equal 5, okay? Now it's ready there, okay? It's ready for that j here. Now, for lambda is equal 5, look at here. I assume, okay, suppose it's 4. So nu is 7 minus 4 is 3. Alpha, the multiplicity is 3. Is 3 minus 3 is equal to 0. No generalized eigenvector. So there is no one here. Okay? That's okay. Now let's do, okay? Let's make j minus 3i. Okay? Look, j minus 3i, I'll just put here 0, here 0, here 0, and here 0. 5 minus 3 is 2, 5 minus 3 is 2, 5 minus 3 is 2. It's 2. There is no one here, okay, because from here, no generalized eigenvector, okay? Let's erase here. It's not clear here. It's still here. Now, this is j minus 3i. It's clear that this block over here we already did. You remember? 0, 0, 0, 1 here and 1 here. For the power 3 of this, okay, if this matrix I put the power 3, the exponent 3, this will be my matrix 0. Okay? Then if I do here, if I write here j minus 3i to the power 3, when I multiply this times this times this, I'll have a big 0 over here. Okay? And this will be 8. Okay? 2 times 2 times 2 is 8. So this I'll raise it, okay? I'll put 0 here and 0 here. So based on what I wrote, okay? I have 0, 0, 0, 1 here and 1 here. This to the power 3, this is 0. That's what I did. I put power 3 over there. And here, okay, is 2 to the power 3. I put 8, 8, 8. 8, 8, and 8. Okay? Now, j minus 3 to the power 3. Now I will work with lambda is equal 5. Okay? Now I work with lambda is equal 5. Let's see what I get. Okay? Look, I'll just put here lambda is equal 5. Then I'll have j minus 5i. Is j or a? Doesn't matter, because j and a, they are similar. So these I'll write like that. Okay? I have two output and then I'll subtract. Okay? This is 4. I'm sorry, it's not 2, it's 3. 3, 3, 3, 3, 5, and 5. I'll subtract 5. So this will be 2. This will be 2, 2, and 2. This is 0, 0. This is 0 and 0. Now is 1 here and 1 here. Okay? Now this is j minus 5i. Now, you see this block here? You see this block here? Okay, do you remember j minus 3i cubed, what was? Okay, let's erase here just a little bit, okay? Do you remember this here? I have, for lambda is equal to, all of this was 0, for lambda is equal to. Then I had here 8 and 8. Do you remember that? So, when I multiply, okay, j minus 3i to the power 3, look how easy, times j minus 5i to the power 1, this will be 0, okay? Because this block here, 0, 0, will multiply 8, 8, will be 0. And this block here, which j minus 3i to the power 3 was 0, multiply all this block here, this is 0, okay? All of this, okay? Then it will be 0. So, j minus 3i to the power 3 times j minus 5i to the power 1 is 0. Then, the minimum polynomial will be, in this case, okay, lambda minus 3 to the power 3, lambda minus 5 to the power 1 is equal to 0. Now, this is matrix, this is scalar. Okay, there's a minimum polynomial for this. Did you understand? So, if I know A, I know the characteristic polynomial, okay, and I know row of each lambda. Why do I know row of each lambda? Because I have my matrix A, okay? I subtract the lambda that appears in the characteristic polynomial. So I know how to count, okay? How many pivots do I have? So I have this and I have this. From this, I build my matrix J. Let's consider the same rank, okay? Row 5, okay? Here's the same, okay? Here not change. But Ni is equal to is a two solution to eigenvector, two blocks, and alpha minus Ni is equal to. Now, the other possibility is before, okay, I put one right here. Now, I put the one right here, okay? And for the 5 is the same, okay? We have 0, no generalized eigenvector for lambda is equal to 5. Now, here, look, Ni is equal to, I have two blocks here, but my blocks are like that. There's this one and this one, okay? And also, for lambda is equal to 5, as we did before, okay, we have in this case, okay, look, let's see here, this is 5 to the power 3, so there is one more 5 here, okay? This is another 5 over here. Okay, this is a 7 by 7 matrix. 3, 6, 7. Okay, 7 by 7. Okay. Now, from here, okay, my nu is equal to 3, so no generalized eigenvector. So I have 0 here and 0 here, no ones. Now, let's see. Look how easy to see it. Let's put j minus 3i to the power 2. Look why. Here will be 0, okay? 0 here, 0 here, 0, and 0, okay? Now, here is in this case, okay, I have 0 here. 5 minus 3 is 2, okay? 2 here, 2, and 2. This is j minus 2i. J minus 3i, I'm sorry, okay? Let's erase here, okay? Look, here I have j minus 3i, okay? J minus 3i, okay? It's like that. Now, look. If I multiply j minus 3i, if I square it, I'll square it, okay? I'll repeat this. Okay, then I have j minus 3i times j minus 3i, okay? This is equal. Now, I have this matrix here, look, 0, 1, 0, 0, That's my block. Here I have another block, 0, 1, 0, 0. Okay? And here I have 2, 2, and 2. Okay? Now, these times the same matrix. Okay? This is the same block here, 0, 1, 0, 0. Here we have 0, 1, 0, 0. Okay, this is my two blocks. And then I have 3 2s here. Okay? Now, if I multiply j minus 3i times j minus 3i, look, this block here times this block here, I will get 0. Okay, because remember, always remember, okay, I have here 0, 1, 0, 0 times 0, 1, 0, 0. This is my matrix 0. So, look, here, j minus 3i times j minus 3i, I will get, I will write here, okay? I'll write here, will be quite clear. I will get, I'll put here, okay? Now, I'll have 0, 0, 0, 0, it is one block. Here 0, 0, 0, 0, that's the other block, okay? Now, then I have, look, if I multiply this by this block times this block is this, okay? And this block times this block is this. Now I have 2 square, okay? Because I'm multiplying those two. I have 4, 4, and 4, okay? Now I have this. This is j minus 2i squared. Now I write for lambda is equal 5, okay? For lambda is equal 5, what is going to happen here, okay? I'll write here, Now let's write for lambda is equal 5. So 2j minus 5i is equal, remember I have 2, 2, 2, then I have minus 3, minus 3, minus 3. And I have, in this case, 4, I'm sorry, there's another 3, there's another 0 over here, okay? Okay, 1, 2, 3, 4, that's okay. It's lambda equal 3, I have 4. Then I have minus 3 here. Here I have a 0 and 0, okay? This is j minus 5a. Now, attention, okay? If I multiply this times this with j minus 3i squared, you see, this block here, I'll put these two blocks, okay, I'll take the blue, okay? Look, this here, okay, this here, that belongs to my lambda is equal 3, okay, here, all this is 0. You see, look at here, I have the 4, okay, I have 4 here, you see, look, you see these? These are different from 0. When I multiply this times this, the whole thing will be 0, you see? I have 3, 5, so there is another 0 over here, okay? Let's put here, 0, 0, 0, 0. So, this block over here, okay, that belongs to lambda is equal 5, will multiply this block over here, okay? Then it will be 0. So, the minimal polynomial for this is quite easy. It will be, I'll write down here, it will be j minus 3i squared times j minus 5i is equal to 0. See, it's different from the last one. The last one, when I have one block, I'll just repeat what I did last time. Okay, the one, okay, I have two blocks, and I put, here's 3, 3, 3, and 3. I put one here and one here. So this block to the power 3, okay, when I subtract from 3 here, I have 0, 0, 0, 0, okay, 0, in this case 0, 0 here, okay? When this block here to the power 3, okay, will be 0, and then I here have another 0 here, okay? Now, this here, okay, this here to the power 3 is 0. That's why before we had j minus 3i to the power 3 times this. But now, because I have still 2 blocks, okay, but the blocks are like this, 0, 1, 0, 0, that's one block, and the other one, okay, 0, 1, 0, 0, okay? From this case, my minimum polynomial then will be m of lambda is equal, now it's the same thing as a minus 3i, okay? It will be lambda minus 3 to the power 2 times lambda minus 5 to the power 1. So that's a minimum polynomial. Attention, okay? The same rule, sure, same ni and same alpha minus ni. I get another minimum polynomial. This is a summary what we have been doing, and this is the characteristic polynomial. So this equal to 0. Lambda is equal to 3 is the eigenvalue. Lambda is equal to 5 is another eigenvalue. This is the multiplicity of lambda is equal to 3. This is the multiplicity of lambda is equal to 5. Okay, now rho for lambda is equal to 3, rho is 5. So ni is equal to 7 minus 5. Remember that this a here comes from the elements of A are the coefficient of the unknowns, okay? Now this is x is a known, c is a known vector. Lambda is equal to 3, rho is 5. So for rho is 5, this is 7 by 7, because 4 plus 3 is 7. Then ni is equal to 7 minus 5 is equal to alpha minus ni is 2. Here indicates 2 eigenvectors, here indicates 2 generalized eigenvectors. The same idea is for lambda is equal to 5. So the rank is 4, ni is 7 minus 4 is 3, alpha minus ni is 0. Then it's here, okay? Now, as I said, these are the blocks. This corresponds to J1. See here, we have here 2 blocks, okay? This 1 block and 2 blocks. 4 lambda is equal to 3. And also we have 3 blocks, you see, 3 blocks for lambda is equal to 5. You see 3 blocks here, okay? And 3 solutions. Now, this is the first choice for J1, okay? Now, we solved and we got for m1 of lambda, this is a minimal polynomial for this J1 is lambda minus 3 to the power 3, lambda minus 5 to the power 1. That's a minimal polynomial. Just compare with this characteristic polynomial. Then here, for ni is equal to 2 also, and alpha minus ni is equal to 2, we have 2 1s here. Here we have 2 1s. Okay, this is another way to represent J, we call J2. Remaining, okay, ni is equal, in this case, ni is equal to, and the number of eigenvectors are also 2. I have 2 1s here. This I have 2 blocks, okay, and this is for the eigenvalue 5, in which ni is equal to 0. That's why we don't have 1 here. Now, on the third case, still we have 2 blocks, okay, because we are not changing this, okay? Now, this ni is 2 blocks, this 1 here and 1 here. This is another block, this 1 block, and this is another block, 2 blocks, okay? Now, for lambda is equal to 5, they are the same. And from here, okay, from this here, m2, okay, the second, this is equal to 0. Let's put a 0 here, okay? Now, m2, the minimum polynomial for this J2 is equal to lambda minus 3 squared lambda minus 5 to the power 1. Look, this minimum polynomial is different from this one. This is lambda minus 3 to the power 3, because you see this block over here. If you subtract 3, okay, and if you take j1 minus 3i, then this one with the power 3 will be 0. So if you erase 3 here and put 0 here, 0 here, and 0 here, okay? Now this, we have two blocks. If you subtract 3 here, you have two blocks, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0. If you multiply this matrix, J, attention, it's not this matrix, J2 minus 3i times J2 minus 3i, the product of this block with itself will be 0, and this one will be 0 too. That's why the characteristic polynomial is the same, but the minimum polynomial is lambda minus 3 to the power 2. Now for the third case, it's similar to this case here, okay? Now this is a block. This block, if you subtract 3, okay, then it will be 0, 0, 0, 0. And this block here, J3 minus 3i to the power 3, this will be 0, as we pointed out before. Then the minimum polynomial for this case is the same of the minimum polynomial for this case. Why? You see, because these are the same blocks, okay, but different from this one. Now, what do you want? We want to solve AX is equals C. So we need 3, in this case, okay? We need 3 parameters, okay? Always. To get the solution of this linear equation, system of linear equation, we want P minus 1, and J. Then what I will do? Okay, now, if I use this J1, I will have P1 and P1, the inverse of P1, to solve the solution for this equation. If we use J2, I have P2, the inverse, and J2. You see, the answer for this system remains the same. Now let's see here. AP1 is equal to P1 J1. So A and P1, they are, A is similar to J1. And this here, A is similar to J2. And A is similar to J3. Okay? Now, let's see here. Look at here. Okay? From here, there's a case 1. I will write here. So, case 1, you have 1 here and 1 here. A operating of P1, P2, P3, P4 to P7 will be something here. Okay? AP is equal P times J1. You see this J1 here is a J1 here. Now, let's multiply this line. Also remember, okay, that P1 is an eigenvector, which has 7 components. P2 is the same. All these vectors, they have 7 components. Why? Because the matrix is 7 by 7. Why the matrix is 7 by 7? You see the multiplicity here. If you add, you have 7. You have 7 in the diagonal here. Now, we are in this case, okay? Look, let's multiply, okay, this row by J1. See? Now, this we have 3P1 is here, plus P1 plus 3P2. P1 plus 3P2. Now, here we have on this row, or this column, you have P2 plus 3P3. P2 plus 3P3. Now, for this column here, if you multiply this row by 3, you see you have here 3P4. Now comes 5. Then you're going to write this row times 5. Okay? You'll be, this case, 5P5. Likewise, this column here, okay? This times this column will be, in this case, okay, we have here 5P6. And the last one, the last 5 here, if you multiply this row by this J1, you're going to have 5P7. Now you see, in terms of this J1, we obtained A times P is equal P times J. Okay? Now, you see, this is P times J1. This is P times J1. That was here. P times J1. From here, and in terms of this J1, you multiply this P times J1, so we obtained, this is J2, I'm sorry. We obtained this one. Now we can see from these blocks here that this here is P2 star. Okay? From here, we obtain here P2 asterisk. Okay? And from here, we have P3 asterisk, which indicate that this is an eigenvector, is one here and one here. Okay? Then P2 and P3, you can see here, okay, correspond to the two solutions. You see, the two solutions here is to generalized eigenvector. Now, let's play, okay, I'm sorry, this is not J2 here, okay? Let's play now the second case. You see J2 here? Okay, J2 here, it has this form. Now, A times P is equal P times J2. This is J2. Okay. Now, we'll multiply now this row times J2. See, look how it's easy, okay? I multiply this P here, this is capital P, okay? The transition matrix times G2. Now, here we have 3P1, it's 3P1. Now, this column here, okay, you multiply the row, you see here P1 plus 3P2. This is P1 plus 3P2. See? Now I will skip from here, you see this column, okay? This will be 3P, this is P2, P3. Now you have here P3 here, okay? I miss here 3P3, 3P3, okay? Now, 3P3. This one here, will be P2 plus 3P3, okay? In this case here, I'm sorry, you have P3 plus 3P4. Look at that. That's a third row, okay? This is P3. And this row here, when I multiply, I have 3P4, which is right here, okay? Now, the rest for the lambda is equal 5 is the same thing, okay? That's what we did before. We have P5, 5P6, and 5P7, which is there. I'm not changing here. Now, why I'm not changing? Because for this lambda is equal 5, nu is equal 3, and there is no generalized eigenvector. That's why I repeat 555, 555 here, and 555. Okay? Now we see here, okay, that P2 is asterisk. But you see, not P3, but P4 is this. It's clear the matrix P on case 2 is completely different from matrix P in the case 1. Now let's see the third case. Okay? We wrote these blocks, the different blocks, because we have 2 as a generalized eigenvector. So we play with the ones here. Now, for the third case, let's multiply P times J3. J3 is equal. Okay? Is equal. Now, here, in this case here, when you multiply this row by this column, we have 3P1. Now we'll write this row, the product of this row times this second column is still 3P2. Now this row times this column. So here is P2 plus 3P3. It's here. And this one, this column here, this is, look, this will be P3 plus 3P4. It's here. So from here we know that this vector here, P2, P3, I'll put the right one, okay? Now here, P3 and P4, they are the generalized eigenvector, just distributing the one right here. Here I put one here and one here, and this one. Okay? Now, this is very important. Why? AP1, the first case, okay, this is P1, is P1 times J1. So P1 times J1 is just this side here, okay, the right hand side. A2 is equal P2 J2. This A, the second case, this is P2. This P is different from that, okay? And this one, this P here, is completely different for the other two, to P. Now we write here. Now I'm ready to calculate for each case, okay, the solution of the equation, because we want to solve this equation, okay? How I will play with the solution of this equation? The same way we did before. Then AX is equal C. A is known matrix and C is a known vector. Now I substitute A, but you see A is equal Pi Ji Pi minus 1. You see, I put I here. I can be 1 or 2 or 3. Sure, okay? I want 1 or 2 or 3. Just work this, okay? The same A, you see? The same A. We have to obtain this. A is similar to Ji. A is similar to J1, A is similar to J2, A is similar to J3. J1, J2, and J3 are completely different as P1, P2, and P3. Now, I substitute A here, so I will have Py, Jy, Py minus 1. X is equal C. Now, this is Pi minus 1, Pi Gi pi minus 1 is equal pi minus 1 times c. Okay, now this is the identity. So here, the next here, okay? This here I call y, okay? Now, this is a vector, the same vector S expressed in the eigenspace basis. Now, ji, in this case, ji yy is equal pi minus 1c. Okay? Now do I get pi or p1 or p2 or p3? Just solving lambda, let's see, lambda 2I x is equal 0. We know here that we will have two solutions. Okay, we know here. And then we will find two generalized eigenvector. From here I have two solutions. So then we'll have here 4, okay? 4 solutions. Okay, look at here. P1, P2, P3, P4. Okay? Now, from here we get the solution, and from here we get two linearized eigenvectors. You see, for case 1, case 2, and case 3, we always have, two generalized eigenvectors. Okay, two generalized eigenvectors. I see this in terms of this. Okay. Now, I will solve this. I have A, and I have also I'm sorry, this is 3. I have A and I have the lambda. For each lambda, I solve this question, the homogeneous equation. Then, for A minus 5I, x is equal 0. This is another matrix, okay? Another matrix. I have all the particular parameters here. Here I know there is no generalized eigenvector. So I'll have 3 solutions here. Okay? Now, I have 4 solutions here. 4. Here I have 2 plus 2 generalized. Okay? Here, this is 4. Here I have 3 solutions. No generalized eigenvector. So I have 7 solutions. You see, here I have 7 solutions. Okay, from these I will get the eigenvector appropriated to each case. Okay, then I have pi and pi minus 1. With ji, I can solve. This is my di. You see, as I said, I is 1 or 2 or 3. No, just 2, see this. Then I'll solve my equation. You see, the unknowns are x1, x2, x3, x4, x5, x6, x7. The unknown doesn't change if I work with I is equal 1, or I is equal 2, or I is equal 3. Okay? Then that's important. So you must understand that the solution of this does not have anything to do with the minimum polynomial. See? Nothing to do. I would like to remind you, for instance, for this case 1, I could exchange the column of this vector P4 and put over here and call it the column, and call it P1. And then this P1 will replace this column here, the components of P1, in which I already calculated, and I put right here. So I change my P on the case 1. I would call P11. Okay? Also, I could exchange this column with this column. Okay, I put the column, the 7 elements of this column, I can put here and call it P5. And P5, the column I put over here, and call it P6. No problem. Then I'll have another P for this case 1, and this and so on. Because we saw when exchange columns, we get another matrix. What is important, as I said, is the number of the generalized eigenvectors. That's what is important. And also the number of the solution of this equation. That's what is important. That is very, for you to realize, if I change P appropriately, the solution of this linear system, the system of linear equation, does not change. That was important. Consider now this case. This is x prime is equal to c prime. Okay? This is another matrix. Doesn't have nothing to do with the previous matrix, on the previous example. Suppose the polynomial characteristic is the same for different matrices. Now, from this matrix here, we know lambda is equal to 3 and lambda is equal to 5 are the eigenvalues of this matrix A prime. Suppose rho of A prime minus 2i is equal, let's say, 6. Okay? Nu of this matrix, not A prime, but the A prime minus 2i. Let's put it here, okay? A prime minus 2i, this is equal 7 minus 6, which is 1. Now, the difference, the multiplicity 4 minus nu is 1, is equal to 3. Okay, suppose for lambda is equal to 5, this remains the same. Rho is equal to 4, nu is equal to 3, alpha minus nu is 0. Okay? Now, what this tells me, this here shows that I have one solution. Solution of what? Of this equation here, a minus 3i x is equal to 0. So the matrix here. Now, I have only one eigenvector. And one block. Here is the same. I have 3 solutions. You have to repeat, okay? 3 solutions and 3 eigenvectors and no generalized eigenvector. So, attention now. From here, okay, I have 3 generalized eigenvector. Okay, now, in terms of this parameter here, we will be able to write J. Only in terms of this parameter here. Okay, in the diagonal, we put 3, 3, 3, and 3. Here's 5, 5, and 5. Look, for lambda is equal to 5, there is no 1 here on the super diagonal. But for lambda is equal to 3, I have 3 generalized eigenvector. So there is no way to play with the ones. That's the only form, okay, that's the only one way to put ones over here. This is 3 ones. Why 3 ones? Because we have here 3 generalized eigenvectors. Now let's see what's going on here. Okay, now let's come to this block. If you don't remember, I will remind you. There's one here, and one here. So this is a matrix 4 by 4. Now, if I subtract, okay, let's call this A. Now, A minus lambda I. Okay? I put Q, let's put 1. This is equal to 0, 0, 0, 0, 1, 1, and 1. There is no other way, okay, to distribute this, the superdiagonal. This is the only solution. I have only one J. Now, let's see here. Okay, if you put here to the power 4, this will be 0. 4 is a minimum exponent such that this matrix here will be 0. Because if you have A minus lambda I to the power 5, obviously this will be 0. A minus lambda I to the power 10 will be 0. So this 4 is a minimal. It's a minimal way, a minimal exponent in which A minus lambda I to the power 4 is equal to 0. This is a minimum number. Now, let's put here A minus 3I, A prime minus 3I. Since A prime and J, they are similar, we can put here J minus 3I. Okay, let's see here. Okay, this will be 0, 0, 0, 0. The 5 minus 3 is 2, 2, and 2. Now, I have 1 here, and 1 here. You see, look at this block here and look at this block here to the power 4. Okay? Now, if I raise here the exponent to the power 4, this to the power 4. So this block here, attention, this is just one block. You see here, one block. Look, I have only one block here. One block. See here? This is one block. From here, we have 3 blocks. 3 blocks. See this block, and this block. 3 blocks. But here's only one block, like that. See? Ni is equal 1. You see one block here? It's here. Now, this block here, this to the power 4, for sure, this will be 0. All this will be 0. All this will be 0. Okay, that's the answer here. This will be a big 0 here. And here, 2 to the power 4 is 16. Okay? 16, 16, and 16. This is different from 0. Now, as exactly what we did before, J minus 5 lambda, J minus 5I is equal, look, this will be 3 minus 5 minus 2, minus 2, minus 2, minus 2. Here will be 0, 0, and 0. Okay? That's easy. J minus 5. This is 5, okay? Subtract 5, it will be 0, 0, 0. Now, if I multiply J minus 2I, 3I, I'm sorry, to the power 4 times J minus 5I to the power 1, you see, this 0 here will multiply this block here, okay? And it will be 0. And this block here, the whole, corresponds to lambda is equal 5. This corresponds to lambda is equal 2. Okay? This corresponds to lambda is equal 2. And this here corresponds to lambda is equal 5. If I multiply this times this will be 0 here, and this will be 0 there. So this is 0. So my minimal polynomial will be lambda minus 3 to the power 4, lambda minus 5 to the power 1 is equal to 0. Now, this is my minimal polynomial. Let's call here m of lambda. This is my minimal polynomial. Look at it here, okay? From this case, you see how rho is important, okay? I could not obtain there less than 4, the exponent less than 4. Why? Because this rho here. But now it's to the power 3, this is to the power 1, with a minimal polynomial. Okay, there is a small correction which will not interfere in the results. Now, you wrote rho, the rank of a prime minus 2i here, okay, is a prime minus 3i because lambda is equal to 3. Likewise, ni a prime minus 3i. So the nullity, I put here 2, is 3 because lambda is equal to 3. This nullity is 7 minus 6 is 1. Everything is correct. And also the number of generalized eigenvector. Everything is correct. Okay, now we can see that I wrote this, and this, this, and this. And here I call lambda is equal to 2. It's not. It's lambda is equal to 3. Okay? Because the eigenvalue is 3 and not 2. Likewise, this here is lambda is equal to 3 and not 2. Okay? That's the only correction. Okay? Because m of lambda is equal, in this case, okay, lambda minus 3 to the power 4, lambda minus 5 to the power 1 is equal to 0. So it's a minimal polynomial. It's just a correction, okay, a small correction, which didn't interfere in the minimal polynomial. Consider now this case. This is x prime is equal to c prime. Okay? This is another matrix. Doesn't have nothing to do with the previous matrix, on the previous example. Suppose the polynomial characteristic is the same for different matrix. Now, from this matrix here, we know lambda is equal to 3 and lambda is equal to 5 are the eigenvalues of this matrix A prime. Suppose rho of A prime minus 2i is equal, let's say, 6. Okay? Nu of this matrix, not A prime, but the A prime minus 2i. Let's put it here, okay? A prime minus 2i, this is equal 7 minus 6, which is 1. Now, the difference, the multiplicity 4 minus ni is 1, is equal to 3. Okay, suppose for lambda is equal to 5, this remains the same. Rho is equal to 4, ni is equal to 3, alpha minus ni is 0. Okay? Now, what this tells me, this here shows that I have one solution. Solution of what? Of this equation here, a minus 3i x is equal to 0. So the matrix here. Now, I have only one eigenvector. And one block. Here is the same. I have 3 solutions. You have to repeat, okay? 3 solutions and 3 eigenvectors and no generalized eigenvector. So, attention now. Attention now. From here, okay, I have 3 generalized eigenvector. Okay. Now, in terms of this parameter here, we will be able to write J. Only in terms of this parameter here. Okay, in the diagonal, we put 3, 3, 3, and 3. Here's 5, 5, and 5. Look, for lambda is equal 5, there is no 1 here on the super diagonal. But for lambda is equal 3, I have 3 generalized eigenvector. So there is no way to play with the ones. That's the only form, okay? That's the only one way to put ones over here. This is 3 ones. Why 3 ones? Because we have here 3 generalized eigenvector. Now let's see what's going on here. Okay, now let's come to this block. If you don't remember, I will remind you. There's 1 here, 1 here, and 1 here. So this is a matrix 4 by 4. Now, if I subtract, okay, let's call this A. Now, A minus lambda I. Okay? I put Q, let's put 1. This is equal to 0, 0, 0, 0, 1, 1, and 1. There is no other way, okay, to distribute the super diagonal. This is the only solution. I have only 1 J. Now, let's see here. Okay, if you put here to the power 4, this will be 0. 4 is a minimum exponent such that this matrix here will be 0. Because if you have A minus lambda I to the power 5, obviously this will be 0. A minus lambda I to the power 10 will be 0. So this 4 is a minimal. It's a minimal way, a minimal exponent in which A minus lambda I to the power 4 is equal to 0. This is a minimum number. Now, let's put here A minus 3I, A prime minus 3I. Since A prime and J, they are similar, we can put here J minus 3I. Okay, let's see here. Okay, this will be 0, 0, 0, 0. The 5 minus 3 is 2, 2, and 2. Now I have 1 here, 1 here, and 1 here. You see, look at this block here and look at this block here to the power 4. Okay? Now, if I raise here the exponent to the power 4, this to the power 4. So this block here, attention, this is just 1 block. You see here, 1 block. Look, I have only 1 block here. 1 block. See here? This is 1 block. From here, we have 3 blocks. 3 blocks. See this block, and this block. 3 blocks. But here's only 1 block. Like that. See? Ni is equal 1. You see 1 block here? It's here. Now, this block here, this to the power 4, for sure, this will be 0. All this will be 0. All this will be 0. Okay, that's the answer here. This will be a big 0 here. And here, 2 to the power 4 is 16. Okay? 16, 16, and 16. This is different from 0. Now, as exactly what we did before, j minus 5 lambda, j minus 5I is equal, look, this will be 3 minus 5 minus 2, minus 2, minus 2, minus 2. Here will be 0, 0, and 0. Okay? That's easy. J minus 5. This is 5, okay? Subtract 5, it will be 0, 0, 0. Now, if I multiply j minus 2i, 3i, I'm sorry, to the power 4 times j minus 5i to the power 1, you see, this 0 here will multiply this block here, okay? And it will be 0. And this block here, the whole corresponds to lambda is equal 5. This corresponds to lambda is equal 2. Okay? This corresponds to lambda is equal 2. And this here corresponds to lambda is equal 5. If I multiply this times this will be 0 here, and this will be 0 there. So this is 0. So my minimum polynomial will be lambda minus 3 to the power 4, lambda minus 5 to the power 1 is equal to 0. Now, this is my minimum polynomial. Let's call here m of lambda. This is my minimum polynomial. Look at it here, okay? From this case, you see how rho is important, okay? I could obtain there less than 4, the exponent less than 4. Why? Because this rho here. But now it's to the power 3, this is to the power 1, which is a minimum polynomial. You see how, to understand or to manipulate, to deal with minimum polynomial, which does not interfere in the solution of this equation, okay? It's you must know about those initial blocks that I showed you, such that when you take j minus lambda I, you see those blocks there, and you know which power, okay, I will be dealing to, such that j minus 3i to the power 4 is 0. I have to know. That's a minimum, okay? And this, observe that AP is equal PJ, and A and J are similar matrix. From here we can get A is equal PJ, P minus 1. Okay, now, let's do what we did previously. AP is equal PJ. This is our J. Okay, let's multiply. Always remember that each eigenvector, it has 7 elements on its column. Okay, each one of these. So this is a matrix, this is a square matrix 7 by 7. And also all the eigenvectors and generalized eigenvectors, they are linearly independent. Now let's multiply, okay? P times J. Don't forget, all this is 0, okay? This is 0 here. So let's put here, this row times this column is 3P1. Now this row times the second column, look, this will be P1 plus 3P2. It's here. Now this row times the third column, this is P2 plus 3P3. P2 plus 3P3. Now this row times the fourth column, this is here, this is P3 plus 3P4. And now for lambda is equal 5, you have here this row times this column, you'll be 5P5. This row times this column will be 5P6. In the last one, this row times the last column will be 5P7. Now we see that this is a generalized eigenvector, generalized eigenvector, generalized eigenvector. So let's put a asterisk here, and here. So you have 3, see? Because ni is equal, this case, ni is equal 1, okay? And then alpha minus ni is exactly 3. That's it. So this P is important for us. If you have P minus 1 and J, okay, then it is implied we can solve AX is equal C. Suppose I have a system of linear equation, AX equals C, in which I want to solve it. See, that's our goal. Okay. Now, suppose the characteristic polynomial is lambda minus 2 times lambda minus 3 times lambda minus 5 is equal to 0. I want to find out, that's a silly question, okay? I want to find out the minimum polynomial for this one, okay? Now, for lambda is equal to, look, I have here the power 1, and power 1. Now, I have a 3 by 3 matrix, because 1 plus 1 plus 1 is 3. So the matrix A is 3 by 3. This matrix A is 3 by 3. Now, matrix 3 by 3. Now, row for lambda is equal to. Now, row of A minus 2i is equal ni of A minus 2i is equal. Suppose it's 3 by 3, suppose row is 2. Ni A minus 2i will be 3 minus 2, which will be 1. What means that? Look, one solution. Solution of what? Of this equation here, A minus 2i, x is equal to 0. This is the matrix. That's one solution. Also, we have one eigenvector and one block. This for j is equal to. Now let's see how many generalized eigenvector do we have. So alpha minus ni is equal. If this the multiplicity of lambda is equal to is 1, and ni is 1, so it's 0, which means no generalized eigenvector. See? You see, How many informations we are obtaining just knowing this here? This is very, very important. Now, let's do the same for lambda is equal 3. Just a repeat, rho of a minus 3i is equal to ni of a minus 3i is equal 3 minus 2 is equal 1. The same thing. One solution, one eigenvector, one block. No generalized eigenvector. The same thing. In the same for lambda is equal 5. Rho of a minus 5i is equal to nu. Let's write here alpha is the same, okay? Alpha minus nu is equal 1 minus 1, which is 0. Okay? No eigenvector, no generalized eigenvector here. Like exactly the same. Okay? A minus 5a is equal 1. 3 minus 2 is equal 1. Alpha minus nu is 1 minus 1 is equal 0. Now, from here, I'm going to write not j, but capital lambda. This is equal to, now, you see, there is no 1. So 2, 3, and 5. There is no 1 here, no 1 here, no 1 here. Let's see, for lambda is equal to, how many blocks do I have? I have one block, just one. Okay, is here. For lambda is equal 3, I have one block here, so it's here. And for lambda is equal 5, I have one block. Just one block there. See? You see the number of blocks for each lambda, which is independent of this, the other lambda here. So this is my diagonal matrix. So we can say that always when you have eigenvalues, distinct eigenvalues, for sure we have diagonalized this matrix A. Now, I'll repeat again. Now, if the eigenvalues of a matrix A, if they are distinct, I have out here power 1. And then for sure, the matrix is similar to diagonal matrix. Okay? That's a very important result. We can check. Look, lambda minus 2i is equal 0, 3 minus 2, 1, 5 minus 2 is 3. How many pivots do I have for lambda is equal to? This is not pivot. This is one pivot. Don't forget that this is 0 here, okay? Don't forget that. I put 3 here. I have one pivot and one pivot. So what is the rank of this matrix? Look at here. Is the rank of matrix A is 2. Likewise, what is the rank of lambda minus 3i? Okay? Now this is 2 minus 3, this is minus 1. 3 minus 3 is 0, and 5 minus 3 is 2. So that's the rank. The rank of lambda minus 3i is 1 here and 1 there. So it's also 2. You see, for lambda is equal to 3. Now, what is the rank, in this case, for lambda minus 5i? Lambda minus 5i. Lambda minus 5i. So this is 2 minus 5 is minus 3. 3 minus 5 minus 2, and this will be 0. How many pivots do I have here? This and this. So the rank of lambda minus 5i is also 2. Now, suppose I put over here rho of a minus 2I is equal 1. Nu will be 3 times 1, which is 2. Okay. Now, this, the 2 degree of freedom means 2 solutions, have 2 eigenvectors, and 2 blocks, just for 2. Now, the multiplicity minus ni, the multiplicity is 1, minus 2 is equal minus 1, You see, this this does not exist, okay? Because how can I have minus 1 generalized eigenvector? How? Doesn't exist. So I cannot put here rho of a minus 2I is equal 1. Okay? And then this must be 2. Why not cannot be 3? Because I said before, okay, look, a minus lambda I, okay, the determinant of a minus I is equal 0. So this matrix here cannot have in this case, 3 columns which are linearly independent. Cannot. Okay? So also the number of pivots of this, not A, okay? This matrix here cannot be 3. Suppose it has 3, which is an absurd. Suppose it has 3. If it has 3, the solution of this homogeneous equation will be unique, will be trivial solution. So that's why we impose the determinant of a minus lambda I is equal to 0, such that we'll never have 3 linearly independent columns here. So it has to be, rho has to be less than 3. So in this case, when we have distinct eigenvalues, f of lambda is 0. This is a characteristic polynomial. Cayley-Hamilton, the theorem, is a minus 2i times a minus 3i times a minus 5i is the matrix 0. And then in this particular case, the minimum polynomial coincides with the characteristic polynomial. So we have here m of lambda is equal lambda minus 2 times lambda minus 3 times lambda minus 5 is equal to 0. They coincide, okay, here.